So you want to make a GPU more powerful than the Titan XP and you want to know how to do it? I think I'm your guy. GPUs are pretty complex. I mean, the GTX 1080 has 7.2 billion transistors, and the Tesla card, the GP100 chip, that one has nearly 16 billion transistors. To give you a comparison, Kaby Lake CPUs have 1.75 billion transistors, which are a rather whole lot smaller. To make it clear, CPUs operate mostly serially, doing one instruction at a time. If you want to know the main differences between CPUs and GPUs and more about how GPUs work, check out my How GPUs Work video. I'll leave a card up above and a link down below for you. But otherwise, as I said, GPUs mostly work in parallel. A GTX 1080 has 2,560 CUDA cores, meaning, at least in theory anyway, it can do at any one point in time 2,560 instructions or calculations at that specific moment. Compare that to a CPU, which your maximum, your desktop core count is currently at 10. I mean, technically with hyperthreading it's 20, but you've got 10 cores available there to do up to 10 calculations at any one point in time. That 2,560, by the way, also doesn't count the fixed function units for texturing and rasterization and the special function units either. This, coupled with a really high transistor count, means that building your own GPU would be very, very tough. Assuming you took electrical engineering, computer engineering, AP physics, and all that sort of stuff, and have an understanding of transistors, resistors, capacitors, chokes, what else did I list? Logic gates, Boolean algebra, all that sort of stuff, then you might just about have a chance. Now, to make it clear, I didn't take any of those courses. I did take electronics, but that doesn't quite prepare you for just the sheer vastness of what a GPU is, and I can't claim to know everything about GPUs either. If you know anything else in this field, please do let me know in the comments down below, and I've left links to all of my sources in the description down below for you to fact check and check out, and just learn a little bit more on. To start off, you could do what PK from Don't Quit Your Day Job did, which is build a general purpose GPU using an FPGA or a field programmable gate array. This is a lot of a simpler method and obviously a lot less power. He used a Raspberry Pi 2 as the host board and created a board that basically outputted a 640 by 480 resolution VGA signal, and that was pretty much it. So yeah, quite a simple GPU. FPGAs make it a lot easier to manufacture and design chips as they are field programmable. So you basically program what logic you want the chip to do. This is still fairly inefficient, and I wouldn't recommend actually, trying to manufacture your chip in an FPGA format, but it is a nice way to kind of get your understanding of how it all works and actually build a GPU that is somewhat functioning, even if it's nowhere near the standard of anything, including the built-in GPU in the Raspberry Pi 2 anyway. So yeah, that's just something to know. There's actually an open source GPU project on GitHub that I've left a link to it in the description down below. So in theory, if you can get your hands on an FPGA board, you could manufacture or at least have your own general purpose, rather simple GPU. Now, of course, do bear in mind that this is a general purpose and a very simple low-level GPU. This wouldn't be playing your games. This wouldn't be doing much more than just outputting a standard resolution and maybe displaying your web browser or something like that. To be able to design your own GPU, not in an FPGA, and actually try and conquer AMD and Nvidia's game, you're going to have to understand how the GPU cores actually work and how they're sort of designed. A simplified way to look at this is to analogize everything into a block of sorts. So you have a block of register memory, a block of L1 cache, you'll have a set of CUDA cores or stream processors, depending on if you're AMD or Nvidia, basically cores that don't do massive amounts of computation, but they are obviously massive in numbers, so they perform a lot of functions simultaneously. You also have a few fixed function units for texturing and rasterizing, and a few other bits and pieces as well. These blocks are then built into SMs or CUs. They're comprised of multiple cores, multiple texture units, cache memory, and all that sort of stuff. For the GTX 1080, each SM has 128 CUDA cores, 48 kilobytes of L1 cache, 8 texture units, 32 load store units, as well as 32 special function units. Pretty complicated, huh? Designing a chip of this caliber would take years for a small team to build, not including the software and drivers that you would need to write to be able to support this type of chip. For the next bit, I'm referring to this TechRadar article, which is somewhat supported by AMD, who talk through the steps, not necessarily designing, but specifically the sort of steps that you go through when manufacturing a GPU. A GPU is designed to meet a feature set called a PRS, or a product requirement spec. This normally takes somewhere between 6 and 12 months for a team of a few thousand engineers to meet. This PRS is a list of the features, up to 1,000, normally in database form, that the GPU has to meet, and once they fully meet this list, they then go on to floor planning and using software to effectively design the chip for them. Floor planning is exactly what it sounds like. It's planning out exactly where the blocks in the chip are going so that they are closely connected to where they need to be and they're not wasting time, and also so that the data doesn't take too long to transmit from one section to another and all that sort of stuff, and that it all actually fits on the die size that they've chosen. As I mentioned, VHDL is a specific programming language designed to help effectively eliminate the need to fully design the chip itself. You effectively program what the chip should do and how the block should be built, and then you have the sort of automated testing procedure that helps eliminate, years worth of testing that you would need to do on what is up to 16 billion transistors worth of connection. Once the program has assembled the chip, it runs through a synthesis, effectively real-world error testing, and once it comes back with a fully complete and checked off, everything works fine checklist, they then send the chip off to be manufactured. Since AMD and Nvidia are both fabless, which means they don't manufacture their own chips, they send the design off to someone like TSMC or GlobalFoundries. I'll leave a link to an article down below that explains this process much better than I can, but to simplify it, they create a mask that they shine ultraviolet light through to effectively burn the design into the silicon. They then do that multiple times and then use copper interconnects to be able to connect everything up. They then cut the wafer up into individual dies and attach those dies to usable chips that are then sent back to Nvidia or AMD. They then speed bin and test the chips so that they know exactly what speed and what type of chip it's meant to be, whether it's a 1080 or 1070, and what speed it's meant to run at. They then send those chips to their add-in board partners, people like ASUS and Gigabyte and MSI and EVGA and XFX and Sapphire. All those companies then get sent those chips to then add, effectively solder them or use the ball grid array, which is small beads of solder under the chip, to then attach them to the graphics card PCBs and sell them as fully functioning units for people like you to buy on the shelf. So I think that's probably a decent enough explanation of how to go about designing and manufacturing a GPU. I think there's some very interesting things. If you were actually interested in making your own GPU, that Don't Quit Your Day Job project is actually a really good start. And of course, as I said, there's also that open source GPU project that if you got your hands on an FPGA board, you could in theory just program the FPGA to be a GPU for you. So feel free to take a look at those if you are interested, but otherwise I kind of think that's it. So thank you for watching. I hope you enjoyed the video and found it useful and informative. If you did, please do subscribe, and the biggest thing you can do to help me is share this video, whether it's on Reddit or whether it's tech forums or just on your Facebook or Twitter feeds or with someone you know. If you can share the video, it genuinely helps, makes the information available to more people and that sort of thing, and all that sort of stuff. So if you could do that, that would be really awesome. And if you want to support me even more, you can use the Overclockers UK and Amazon affiliate links in the description down below. Just click the link before you buy stuff, and that helps me out. Doesn't cost you anything, and of course, it's easy to do, so that's always nice. But yeah, other than that, feel free to leave a comment and let me know what you thought of the video and if you learned anything new. Of course, if you know anything else about this topic, and especially if I got anything wrong, please do let me know in the comments down below. I'm 20, I don't have a degree in anything. This is all research that I've done just based on trying to learn this sort of stuff, and I'm sure that there is plenty of knowledge gap in my knowledge. So if you could let me know anything that I don't in the comments down below, that would be great. And otherwise, yeah, hope you enjoyed the video. Thank you for watching. Don't forget to, as I said, subscribe, like, and leave a comment and let me know what you thought and all that sort of stuff. And yeah, check out some of the other informative videos. I'll leave a few playlists over here, and of course the subscribe button over there. The few videos that I recommend are the how GPUs work, and also the CPU ones as well, the state of the CPU market, the state of the GPU market, and all that sort of stuff. So yeah, thank you for watching, hope you enjoyed it, and we'll see you all in the next video.